the idea of a geometric mean. This is a new concept. When we talk about the mean of two numbers, you're usually going to think of the arithmetic mean, which is what we use in midpoint formula and stuff like that, adding and dividing by 2, or if there are three numbers, we add and divide by 3, or so on and so forth. Geometric mean is different. Geometric mean is, one way it's explained is by a proportion, another way is through multiplication, because you get the same thing. But basically the geometric mean, instead of adding and dividing by 2, if we have the numbers are A and B, sorry, a little delay on the smartboard there, numbers are A and B, the geometric mean can be found by taking the square root of A times B. So instead of adding and dividing by 2, we multiply and take the square root. That's a geometric mean. It is not the same as an arithmetic mean. For example, if I have, let's just think of, say, 3 and 12. Okay, say number 3 and 12. The arithmetic mean between 3 and 12 is 3 plus 12 over 2, which is 15 over 2, 7.5. The geometric mean is 3 times 12 square root. 3 times 12 is square root of 36, which, fortunately for me, simplifies just to plain old 6. So I can see very quickly that the arithmetic mean and the geometric mean are different. So that's geometric mean. Again, it can also be explained through proportions. If we put the x's on one diagonal of a proportion and the two numbers we're finding the geometric mean on the other diagonal, we come up with the equation that gives us this as well. So geometric mean not so fine, or not so bad. Geometric mean between 24 and 48, kind of big numbers, so that would be the square root of 24 times 48. And I think that's going to be a pretty big number, so 24 times 48 is 1152. And we need to simplify that. What perfect square is going to go into 1152? Well, 1152 divided, is that a perfect square by itself? We check and see. No, it's not. So we start by dividing it by 2. That's 576. The square root of 576 does work out. Square root of 576 is 24 root 2. Now, one way we probably could have done this a little easier is is in the original form, just mathematically. If I'd have noticed here that, 48 is 24 times 2, I could say this is square root of 24 times 24 times 2. Actually break it down a little bit. And the square root of 24 times 24 is just 24 times the square root of 2. So a little bit of a shortcut, because I got 24 times 24 under there. I could have probably recognized that a little more quickly. But it's a little more advanced technique. Not everyone's going to be able to roll with that right now, and that's okay. You can just do the normal multiply and simplify rule. Now, why are we talking about geometric means? Why is this important? Well, with our altitude to a triangle problem, there's an alternate way of solving these. And it involves geometric means. Basically, what it comes down to is, if I take, starting at the right angle here, if I take any individual segment coming from that right angle, I call them kind of like spokes out of a wheel. It wouldn't be a very round wheel. Okay? So any three of these segments. The length of any one of those segments can be found by finding the geometric mean of segments along the hypotenuse. And there are three segments along the hypotenuse. They are AD, DB, and the whole thing AB. The one thing that all three segments will have in every equation that they will have in common is they will always share one of these 3 points. And the equations are given here, but we're going to go ahead and give it on a separate page as well. So I want you to see this. It's a very visual thing. Now, not everybody does these problems using this technique. You may certainly and are perfectly welcome to go ahead and use the drawing three triangles techniques to solve triangles like this. You do not have to use a geometric mean method. But I'd like you to know that it's available because some people like it a whole lot better. It is pretty quick, and it saves a lot of time over drawing all the triangles every time. But you have to really get it in order to use it. The concept of geometric mean is going to be on the quiz probably for everybody, but this particular technique of solving will not be. So let's take a look at this. Let's go ahead and draw ourselves a right triangle. I'm going to choose this one. Okay, there's a right triangle. We're going to draw in the altitude to the right angle. That didn't quite come out right. I'm going to move that around a little bit and make it nice. There we go. Make that a right angle, make that a right angle. Now, I'm going to label my segments. My segments are going to, instead of labeling the points, I'm actually going to label the segments themselves. Okay? And call these A, B, and C. And call this little bit X from here to here. And call this bit from here to here Y. And the whole thing I'm going to call Z. Okay? And the way these geometric mean relationships work is, again, the three that come out of the main big outer right angle that are not at all collinear are the ones that are always by themselves. It's A equals, B equals, and C equals. The geometric mean of, so square root, of the two segments along the hypotenuse that share the endpoint with the segment. So A, let's take a look at A first. A goes from here to here. Now, it does have an endpoint here at the down at the bottom, has another endpoint here at the top. We're always going to be interested in the endpoint that's on the main hypotenuse. Okay? We're always going to be interested in this endpoint. What two segments share an endpoint with right here, right at this spot? Well, X does and Z does. And A is going to be the square root of X times Z. B, segment B here, of course, has endpoint here at this main right angle. That doesn't interest us much. It has an endpoint here on the main hypotenuse. And what two smaller segments share that endpoint? Well, X does and Y does. I think you see what's coming right now. C, again, has endpoint right over here, which is interesting. Here's the interesting endpoint. Which two other segments share an endpoint here? Well, that would be obviously Y and Z. And these are my geometric mean relationships for solving parts of unknown triangles. It's not too bad. Excuse me, I think I'm going to sneeze. Sorry, that's probably loud in the microphone, but probably not as loud as a sneeze would have been if I'd have sneezed in the microphone. Sorry. So let's go ahead and use that. Let's set it up. So here I'm going to notice, what segment am I working with? Of my special ones, it's this X here. And where's the endpoint I'm interested in? It's right there. What two segments go with us? The 3 and the 6. So very simply, instead of drawing three triangles to find out and labeling everything to find out what X is, I can just simply say X is the square root of 3 times 6, which is the square root of 18, which I then simplify. And I found the value of X. That's way faster, I think you'll agree, than drawing out three triangles. I mean, I could draw out three triangles. I'm going to get the same result. I'm going to get X over 3 equals 6 over X, or something like that in my proportion when I draw out those triangles. It's fine. I could do it. I could draw mama triangle, papa triangle, mama triangle, baby triangle, and we get the same solution. But this is a little quicker. Here, my obviously key segment, hopefully obvious, is Y. And my endpoint that I'm looking at is there. So I'm never looking at the endpoint that's at the main right angle. It's always on the hypotenuse. What two segments share that endpoint? Well, the 2 does, so y is the square root of 2 times, and now I have to be careful. 5 is just a segment running along there. I want the whole side. 5 does not have an endpoint. Okay, 5 just runs from here to here. I need the whole thing. So how long is that whole thing? Well, 2 plus 5, or 7. Square root of 14, which does not simplify. So clearly, much faster than drawing 3 triangles. But if you don't see it, it really doesn't work very well. Most people still draw the 3 triangles. Okay, I'm going to tell you that right now. I'd say 80 to 90% of people draw the 3 triangles and work with it that way to solve this. They won't do this. What they would do is they would draw their Papa triangle, Mama triangle, baby triangle, and say, okay, my Papa triangle, I got the hypotenuse is 7, the short side is y, and that's all I know. The Mama triangle, I know the long leg here is 5, but I don't know anything else. Baby triangle, the short leg is 2, the hypotenuse is y. Aha. Most people do it this way, and then they'll say, okay, obviously I'm using first and third here. Second doesn't help me. 7 over y equals y over 2. So y squared equals 7 times 2. So y equals the square root of 7 times 2, and I think you see where we're going with it. Yeah, it's a little more work. We get the exact same answer. Most people do it that way because it's easiest. But it's not necessarily fastest. The geometric mean thing is a little faster. All right, so 2 questions for you today. First off, just a quick check. What does the geometric mean between 12 and 27? Give that in the simplest radical form. I'm going to do another one for you. Hopefully you got that right, but if you didn't, geometric mean between 16 and 18. That'd be the square root of 16 times 18. And 16 times 18 is not something I have necessarily memorized, so 16 times 18 is 288, which is the square root of 144 times square root of 2. 144 times 2 is 288, or 12 root 2. Just going back, in case you missed this, this would be the square root of 12 times 27, which is the square root of 324. Now, what perfect square goes into 324? Well, 3 plus 2 plus 4 is 9. So that means 9 goes into that evenly, which is 36. Wait a minute, 324, that's a perfect square. I think. Yes, 18. Perfect square. So if you missed that one, there was the error. How about this one? Find the value of x in the triangle to the left. You may use either a geometric mean technique or you may use a Papa, Mama, Baby triangle technique. It doesn't matter to me, but go ahead and work on that. And when you're done with that, the podcast is over, and we'll see you in class.